Welcome to Mathematical Structure for Computer Science. And this is CS113 course, also known as Discrete Mathematics. So in these lectures, we're going to cover our textbook, chapter 11, which is trees. So 11-1, we're going to discuss about the basic concept of trees, especially applied to computer science. So our main objective is to go through what is a trees, also rooted trees, trees as a models, and also the properties of trees. So we start with the definition first. We can see from the definition, graph is normally related to trees. So when we have a undirected graph and they are connected together, it becomes a tree. So here we see a tree is a connected, undirected graph with no simple circuits. So example is given here, which of these graphs are trees? We can see that G1 is a tree because we don't have no simple circuits and all the vertices are connected. Also G2 is a tree because all the vertices are connected and there's no any simple circuits. But when we look at G3 and G4, they are not trees. The reason why G3 is not a tree because we can see that the vertex YB, A, D, and Y is a simple circuit. A simple circuit means we have a full connection. So when we look at Y, B, D, Y, they are all connected together. So Y, B, A, D, Y, they are all connected. Again, Y, B, A, D, Y. It's a circuit. It's a simple circuit. So because we have a simple circuit, it's not a tree. So here we can see in G1, there was no any connection in all the vertices to close a loop and more or less to have a circuit, So it's a tree. G2 also, all the vertices again are connected. We don't have any simple circuit, so it's a tree. But here, when we look, we have a simple circuit means all the vertices are, when we start, for example, I start from E, I'm going to end at E. And there's an edges that will start from E and it will end at E. So that's a simple circuit. Again, when we look at G1, any vertex that I start from and I go through the edges, I cannot come back to the same vertex again. Actually, A, we can see there's no any connection between B, so we can't come back. B also the same thing, D, F, there's no connection with B, so we cannot. But when we look at, again, G3, when I start from E, I can go to D and go to A and go to B and come back to E again. So that's a simple circuit. Now the G4 also is not a tree. The reason why, because not all the vertices are connected. So A is not connected. We can see that we have A to F, but there's no connection on A to F to C, E, B, D. So we say G4 is not a tree because it is not connected. So we have like AF by itself, then C, E, D, B by itself also. So here we have the definition of a tree. Here we say a forest is a graph that has no simple circuit, but it's not connected. Now, each of the connected components in the forest becomes a tree. So we can see example of one, this is a tree. Second, the second diagram also is a tree. We can see all the connections and there's no simple circuit. Or the tree, there's no simple circuit, but all the vertices are connected. So always a graph is related to trees. So we have a theorem here saying that an undirected graph is a tree if and only if there is a unique simple path between any two of its vertices, which means there's no simple circuit. There's only a simple path between any two of its vertices. Now, to prove this, we say we are assuming that T is a tree. Then T is connected with no simple circuit. Hence, if S and Y are distinct vertices of T, then there's a simple path between X and Y. And we will discuss this theory. Yeah, we discussed this theory in section 10.4 when we cover graph. That's chapter 10, section 4. So this path must be unique. For if there were a second path, then there will be a simple circuit in T. And also there's a unique simple path between any two vertices of a tree. Now we should assume that there's a unique simple path between any two vertices of a graph T. Then T is connected because there's a path between any two of its vertices. Furthermore, T can have no simple circuit, since if there were a simple circuit, there will be two paths between some two vertices. Hence, a graph with a unique simple path between two vertices is a tree. Exception is if it's a simple circuit. A simple circuit again means the vertex that we start, we can end it there. There's the edges that make it possible that anywhere we start in the vertex, we end it at the same vertex. So that would be a simple graph and it's not a tree. But a simple path between edges and between vertices, again, are trees. So we also have trees as a models, especially trees are used a lot in computer science. In computer science also, we have a tree data structure, which normally the data is organized in a hierarchical form. In computational biology also, species can be arranged in hierarchical form, in the form of tree. Parents at the top, children are down. And the ancestors are top, the descendants are down. Ancestors and descendants of any species. So trees are used as models in computer science. Not only as a models in computer science, but also as a data structure in computer science. Chemistry, geology, botany, psychology, and many other areas. Any application that we need our data or our materials to be in a hierarchy form, it becomes a tree. So example, we can see butane, it's a chemical structure. We are using tree form. So trees were introduced by a mathematician named Cayley in 1857 in his work counting the number of isomers of saturated hydrocarbons. So this is in chemistry field. The two isomers of butane are shown at the right. So we have the isobutane and butane, and we can see the chemical structure is organized in a tree form. So the organization of a computer files, this is very common in computer science, especially the web, the way data is organized in the web, and also how the webs are linked together. Most of the time it's in hierarchy form. So an organization of a computer file system into directories and subdirectories are files files is naturally represented as a tree. It's a tree structure. More or less, look, the parents will be at the top and the subdirectories will be the children down. So trees are used to represent the structure of organizations also. So that's the example we give. We know the top will be the president, so the president will be the root of the tree. Then the second command, we have the vice president in each department or each section. Then each vice president may have some sections also that it manages, and that will be the children of vice presidents. So the structure again here is a tree structure. Now we have different types of trees. So we start with the rooted trees, which is more common. A rooted tree means a tree that have one vertex as a root. One vertex as a root. So the root will be like the parent, the mother of all the vertices. So here we say a root tree is a tree in which one vertex has been designated as the root and every edge is directed away from that root. So when we look at the second diagram here, this is a tree. The root is A because we can see that from A, the direction have to go down. It doesn't go up. So that's what we call the hierarchical form. So if A is the president, it's not going to have a supervisor or any person. He's the boss. He's the leader of the company or the organization. So everything will be directed down. So A is the root, and you have a children of B, C, D. B also have children of F, G. Normally B, we use the term as inner node. An inner node or vertex is a vertex or node that has a parent and also have children. Now the FGE is only, they don't have no children, which we use the term leaf, the leaf of the tree. The third one here also is a tree with one root. The root is C, as we can see the direction. But the first one is a tree also. There's no simple circuit here. If, for example, D is connected to F, we may have a simple circuit, then it's not a tree. But as we can see, this is a tree. But this is not a rooted. Normally in computer science or most of discrete mathematics application, the root of the tree is at the top. But we know in the real life, the root of a tree is at the ground, the bottom. So when we look at the top, we have F and G. The root should be only one vertex, not two. And the rest will be directed away from it. So we can see, again, the second diagram. The root is A, arrow is going down. It's not going towards A, it's going away from A. Same thing, the third, the root is C, arrow is going away from C. So the terminology for root trees is a mix from botany and geology, such as these family trees of Bernoulli family of mathematicians. So here we can have the root tree will be Nicholas, born 1623 to 1708. Then they have children Jacob the First, 1654 to 1705. Then we have Nicholas. So Nicholas will have three children. Then Joan one have three children also. Nicholas, the second Nicholas have only one child. So again, this is a rooted tree. Now we also say that if the V is a vertex of a rooted tree other than the root, the parent of V is the unique vertex U such that there is directed edge from again U to V. when U is a parent of V, then we call the V as a child of U. So vertices with the same parent are called siblings. So here, Jacob 1 and Nicholas and Johann 1, they are all siblings. And Nicholas at the top root have 3 children. Then the same thing applies to Johann. Johann have 3 children, but Johann is a sibling to Nicholas. And Nicholas too is also a sibling to Johann too. So we say a vertex of a rooted tree with no children is called a leaf. So here, Johann 3, Jacob 2, Nicholas 2, Nicholas 1, and Jacob 1 are all leaf trees. So a leaf node is a node or a vertex that has no children. And also we can say Nicholas 1, mother or parent is Nicholas, and Nicholas' parents is another Nicholas. So we have the descendants and the ancestors. So the ancestor will be Nicholas at the top, and Nicholas' descendants will be Nicholas and Nicholas 1. Or Johann can be 1 also. Johann 1 can be the descendants of Johann 1 can be Nicholas, excuse me, Nicholas 2, Daniel, and Johann 2. Johann 2 descendants can be Johann 3 and Jacob 2. Jacob 2 ancestor will be Johann 2, and Jacob 2 ancestor also can be Johann 1. So here we're learning the terminology. What is a leaf? A leaf would be the vertex or node that have no children. Also, we have an inner node or inner vertex, which is a vertex that have a parent and also have children, has a children. Then we talk about the ascendants and descendants. And the siblings means the vertices are in the same level. So every tree from the root to the leaf, the longest leaf is what we call there will be a path. So for example, I can go from Nicholas to Johann 1 to Johann 2 to Jacob 2. So that's a path of the tree. And also we have what we call the level of a tree. The root normally is level 0. The second will be level 1. Third will be level 2, level 3. So now if I want to find the height of a tree, it will be the number of levels plus 1 if I start the level from 0. Some textbooks may start the level from 1, that's the root. If I start the level from 1 as the root, then the height is the same as the number of levels. But if I start the level from 0, the height of the tree will be the number of levels plus 1. So here we also say that if V is a vertex of a rooted tree other than the root, the parent of V is the unique vertex U, such that there is a directed edge from U to V. So it will go towards V from U. Now, while U is a parent of V, then V will be called a child of U. Now, vertices with the same parent are called the siblings. So we say Nicholas 2, Daniel and Johann 2 are siblings. Also, we talk about the descendants. Descendants will be the children. And also, we have the path. And also, we have the leaf. Leaf will be the vertices with no children. So example will be Nicholas 1 or Jacob 1. And that's the leaf. The path normally is the edges that we visit, same as graph. So we want to go through some of the terminology for the rooted trees here. So we have an example here saying that in the rooted tree T with a root A, we are talking about the diagram here, the root is A. Find the parent of C. Okay, let's do that first. The parent of C, so C is here. So the parent of C will be B. Then they say we should also find the children of G. So what is G? Okay, G is here. So G have 3 children. H, I, and J, 3 children. And then the siblings of H. So we look at H, the siblings of H will be the same level of the vertices. So it will be I and J. And as ancestors of E. So we go to E. The ancestors will be C, B, and A. So let's go through the answer one at a time here. So the parents of C is B, as we said. The parents of C, because I'm C here, is B. The children of G are H and I. So the children of G, which is here, the children of G, which one we have here? The children of G are H, I, and also J. We have 3, H, I, J. Now the siblings of H will be I and J because this is H, I, and J. Siblings means all the vertices are the same level. Now the ancestors of Y, so what's Y? This is the ancestors of Y will be CBD. Oh, sorry, CBA. The last one is A. So we have the ancestors of Y is C, B, and A. Now the descendants of B, so we go to B, will be D and Y. So it will be C, D, and E. Descendants of B will be C, D, and E. Now they say we should find all the internal vertices and all leaves. So internal vertices are the vertices that have both children and parents. So one internal vertices, the internal vertices are A, B, C, D, G, H, and J. And you can see that we don't have no leaf. Only the leaf will not be internal vertices. So internal vertices will be all the vertices except the leaf. So we have, there's no, when you look at the internal vertices, we don't have no D. We don't, that's D is a leaf. E, we don't have no E. We don't have no K. We don't have no L. We don't have no M. Then those are the leaves. So the next question, the leaves. So internal vertices are all the nodes except leaves. And the leaves are the nodes or the vertices that have no children. So it will be D, E, K, L, M. And also, no, sorry, and also I here. Now we can also display the subtree rooted at G. So we have this, and they say we should display the subtree of the tree that is rooted at G. So G is right here. So I'll use G as my root, and the rest of this can be, because they are all descendants of G, and that's what we have. The question says, what is a subtree rooted at G? Same thing, they say, what is the subtree rooted at, let's say, B? Then it will be B, then C, then D, then E. So we also move to the next m-Ary rooted trees. M-Ary rooted. So what we mean here is that a rooted tree is called an m-Ary tree if every internal vertex has no more than m children. So example would be a binary tree. A binary tree means the internal vertices have exactly 2 or less children. You can't go more than 2 for binary, the children. So the m-rooted tree depends on the number of children each vertex have. So we say the rooted tree is called an m-Ary tree because every internal vertex has no more than m children. So the tree is called a full m-Ary tree if every internal vertex has exactly m children. So it becomes a full m. So we can have a full full binary tree, which means all the vertices has exactly 2 children, not less than 2, not more than 2. So this is example given here. And the question said that the following rooted trees full m-Ary trees for some positive integers. So solution for T1 is a full binary tree because we can see each of the internal vertices has 2 children. Now for T3, we can see they all have three children. From the root have 3 children, each node have 3 children throughout. So that would be trinary, or normally we use the term trinary tree. Then the next one, let's see, we have 4, no, we have 5 children, 5 here also, 1, 2, 3, 4. Okay, so this is also means we are in 5-nary tree because all the node or the vertex that have children, they have exactly 5. But T4 is not a full binary tree. Why? We can see the root have 2 children, and this vertex or node have 3. So some of the node have 2 children, some have 3 children. So it cannot be a full m-Ary tree. We also have what we call the ordered root trees. So here we say an ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. So they are in sequential order or sorted. So we draw ordered rooted trees so that the children of each internal vertex are shown in order from left to right. So a definition is we have a binary tree. It's an ordered rooted tree where each internal vertex has at most 2 children. Now, if an internal vertex of a binary tree has 2 children, the first is called the left child and the second is called the right child. And the tree will be rooted at the left child of a vertex. It's called the left subtree of this vertex. And if it's rooted at the right side, we call it the vertex, the right subtree of the vertex. So example we should consider here, we have a binary tree T. The reason why we know this is binary tree because each vertex have 2 or less children, 2 or less. So here they say, what are the left and right children of D? So I'll go to D, the left child will be F, the right child will be G. Now, what are the left and right subtree of C? So the subtree of C, you can see the right child will be to the right. So I, L, M. To the left, we have IK. So here we say the left child of D, as we said earlier, is F and also G. Now the left and right subtree of C are displayed in B and C. So this is B, as we said earlier. The question said, what are the left and right subtree of C? So go to C. The left side will be only H and J, so H and J. And then right side will be I, K, L, M. IKLM. So IKLM will be the right subtree of C. In this case, we consider C as our root. So to the right will be LKLM. Or I, sorry, this is IKLM. So what are the properties of a tree? We say a tree with n vertices has n minus 1 edges. So if I have a tree with 20 vertices or nodes, it means I'll have 19 edges. We can prove this by saying that when n equal to 1, a tree with one vertex has no edges. Now, when n becomes 2, which means we have 2 vertices, we may have 1 edge. If it's 3, we may have 2 edge. And that's for a tree, because a tree, remember, we said all the vertices are connected, but there's no simple circuit. That means where we start from, we cannot end over there going through the edges. Now, how do we count vertices in a full m-Ary trees? We say a full m-Ary trees, m-Ary tree with I internal vertices has n equal to mi plus 1 vertices. So every vertex except the root is the child of an internal vertex. Now, because each of the I internal vertices has m children, we're going to have the number of children m times the number of I vertices. So it will be m times I. So hence the tree will contains the number of vertices will be n equal to mi plus 1. M is the number of children, and times internal node, then plus 1. So the next theory is a full m-Ary tree with n vertices has I equal to n minus 1 divided by m internal vertices. So this means if I have a full m-Ary tree with n vertices, it will have I equal to n minus 1 divided by m internal vertices. And the length, or L, will give me n minus 1 times n plus 1 divided by m leaves. So I internal vertices has n equal to mi plus 1 vertices, and L equal to m minus 1 times I plus 1 leaves. And L leaves as n equal to ml minus 1 divided by m minus 1 vertices. So next is solving for I in n equal to mi plus 1. From our third theory in the previous slide, we know that I equal to n minus 1 over m. M is the number of children, n is number of vertices. We want to find I. So each vertex is either a leaf or an internal vertex. So n equal to L plus I. Now by solving for L and using the formula for I, we see that L will give us n minus I, which will give us n minus 1 divided by m. And that will give us n minus 1 times n plus 1 divided by m. So here we have the levels. So here also we have the so again the level of vertices and the height of a trace. As we said earlier, for example, if we have a tree here, the number of levels will determine the height of the tree. And normally, if we start the level from 0 as the root, then the height will be 0 plus the number of levels. So for example, in this graph, we have 0, level 0, B, J, K is level 1, C, E, F, L is level 2, D, G, I, M, N level 3. So this tree have 4 levels, and we go up to the longest one. So even we have only 1 at the 4th, we still count it. So if this is the 4th one, we start from 0, 1, 2, 3, 4, then the height will be 5. Or if we start from 1 as the root, then the height is the same as the number of levels. So here they say when we are working with trees, we often want to have a rooted trace where the sub-trace at each vertex contains paths of approximately the same length. Now, to make this idea precise, we need some definitions. So first, we talk about the level of a vertex, V. In a rooted tree is the length of the unique path from the root to the vertex. Now, that's the level. Then the height of a tree is the maximum of the levels of the vertices. So here in this section, we are going to start the root as 0. So for example, the question says find the level of each vertex in the tree to the right. So root A, the level is 0. Then B, J, K is 1. And C, so again, we have up to 4 levels. H is 4. So A is level 0. B, J, K, level 1. C, E, F, L, level 2. D, G, I, M, N, level 3. Then H is level 4. Now the height is 4, since 4 is the largest level of any vertex. Now in some textbook, they will tell us that the height is 1 plus the level, especially in computer science data structure. We say the height is again the number of levels plus 1. Right here again, the height is the largest level of any vertex. So since the highest number of levels is H, then H will be the level of H will be the height. So in this case, H is 4, the height will be 4. Also, we have what we call the balanced m-Ary trace. So a tree is balanced. The concept here said if we have a rooted M tree of a height H, the tree is balanced if all the leaves are at level H or H minus 1. So now the question said, which of the rooted trees shown below is balanced? Now we look at the definition. The definition of a balanced tree means all the leaves end at the same level. So we can see that T1 and T3 are balanced, but T2 is not balanced because it has leaves at levels 2, 3, and 4. So again, T1 and T3 are balanced. But we can see T2 is not balanced because it has a leaves. A balanced tree here, we can see the question, the definition said a rooted m-Ary tree of a height H is balanced if all the leaves are in where? The height, and also 1 step up. So which means here we can see T3, all the leaves are in the height h. We don't have anyone h minus 1. But T1, we have h, and also we have h minus 1. We have some leaves here also, which is h minus 1. But the reason why T2, in T2 also we have h minus 2, no. So h minus 2 is not balanced. All the leaves must be in h or h minus 1, not h minus 2. So that's why T1 and T3 are balanced. So a balanced tree, a rooted balanced tree means all the leaves are in the height, the lowest, which is the height level of the tree, or h minus 1, height minus 1, which will be the second highest level. So next is the bound for the number of leaves in an m-Ary tree. So here we say there are at most m to the power h leaves in an m-Ary tree of height h. So if the height is 3, then the most leaves we can have will be, remember m is the number of children. To go up to, if it's m is 2, then 2 to the power h. If the level is 4, then 2 to the power 4. So there are at most m to the power h leaves in an m-Ary tree. So m tell us the number of the most children. For example, binary tree means we can have at most 2 children for each vertex. So the most children I can have in a binary tree, if the height is, let's say 5, then it will be 2 to the power 5, because each node will have 2, 2, 2, 2 throughout. Now we can prove this by using the induction method. So the basic step, we say consider an m-Ary tree of a height 1. So we start with the lowest, the basis 1. And the tree consists of a root and no more than m children, all leaves. So it will be 2 to the power 1. Hence, we get m to the power 1. And the height, because the height is 1 at the root. So the root can have only 2 children. 2 will be, m will be 2 because it's a binary tree, or well, we didn't consider it. So it's, let's say, m tree. If it's m tree, it means we cannot have more than m children. So it will be m to the power 1. Now, if it's a binary tree, then it will be 2 to the power 1. Otherwise, we assume the result is true for all m-Ary tree of the height less than h. Now, let T be an m-Ary tree of a height h. So the leaves of T are the leaves of the subtree of T. We get when we delete the edge from the root to each of the vertices of level 1. And that's what we are trying to get. So we have a root with first, second, third, up to 4/5, the amount of subtrees. Now we say that each of these subtree has a height less than or equal to h minus 1. Now, by inductive hypothesis, each of these subtrees has at least m to the power h minus 1 leaves. Since they are at most m, because we remove the root, that's why we say h minus 1. So this will be the conclusion of our introduction to trees. Again, what we cover here is what is a tree in discrete mathematics, and some few terminology, the children, siblings, descendants, ancestors, and number of children, a tree can have will tell us whether it's binary, ternary, m-Ary, true, etc. So again, wish everybody the best. If you have any question about the lectures, you can again send an email or you can contact me. Thank you.